A B tree is a beautiful thing. Keys laid out on disk in sorted order, every lookup a few hops, every read fast. But writes are a different story. To insert a new key, the database has to find its slot, which sits on a specific disk page. Insert another key, and the slot is somewhere else entirely. So a stream of writes turns into a stream of random seeks. The disk arm flails. The SSD's flash translation layer churns. Each insert costs a real, painful disk operation. Random writes are the slow path. On a spinning disk, they are roughly 100 times slower than sequential writes. Even on flash, they cost write amplification, garbage collection, and shorter device life. This is the price B trees pay for keeping data sorted on disk. And it's the problem the log-structured merge tree was invented to solve. In the next 10 minutes, we'll see exactly how. Here's the core trick. What if a write never touched disk on the hot path at all? You buffer it in memory. The user gets an acknowledgement immediately. The database returns. No seek, no slot to find, nothing. Then, much later, when the buffer fills up, you flush the whole thing to disk in one big sequential append. One contiguous block, written in order, no random I/O anywhere. This is the trade. Sequential writes are 100 times faster than random writes on rotating disks, and dramatically friendlier to flash storage too. By batching writes in RAM and flushing them sequentially, an LSM tree turns the slow path into the fast path. There's a catch. Reads now have to look in two places, the buffer in memory and whatever has been flushed to disk. We'll deal with that. But the headline is simple: writes never seek, writes never wait. The in-memory buffer is called a MemTable. It's a sorted data structure, usually a skip list, sometimes a red-black tree. Insert is logarithmic, and the keys stay in order so we can flush them sorted later. Now there's an obvious problem. Memory is volatile. If the server crashes before the MemTable flushes, every write since the last flush is gone. The fix is the write-ahead log. Every incoming write does two things. It updates the MemTable in RAM, and it appends one entry to a log file on disk. The log is purely append-only. No seeking, no slot finding, just sequential bytes at the tail of a file. If the process crashes on restart, the database replays the log to rebuild the MemTable. Durability without random I/O, that's the whole reason it works. So the cost of one write is roughly one in-memory insert plus one sequential disk append. That's the hot path. The MemTable can't grow forever. Eventually it hits a size threshold, often a few megabytes. When it does, two things happen. The current MemTable is frozen, it stops accepting writes, and a brand new empty MemTable is swapped in to take over. Incoming writes never block. Then the frozen MemTable is flushed to disk. Because the keys are already sorted, the flush is one big sequential write. The output is a file called a sorted string table, or SSTable for short. It's just a sorted list of key value pairs on disk. The crucial property is immutability. Once an SSTable is written, it's never modified. Not for updates, not for deletes, not for anything. If you want to change a key's value, you write a new entry that overrides the old one in a future SSTable. So over time, the disk fills up with a stack of these immutable, sorted files, each a frozen snapshot of one MemTable. Now reads get harder. The latest value for a key might be in the MemTable, or in the most recent SSTable, or in any older SSTable. We don't know in advance. So a point lookup walks them in order, newest to oldest. First the MemTable. If we find the key there, we're done, that's the freshest value. If not, check the most recent SSTable, then the next, and so on. The first hit wins. We never read older versions because anything newer overrides them by definition. The best case is a hit in the MemTable, which is RAM speed. The worst case is a key that doesn't exist anywhere. We have to check every single SSTable to be sure. 5 files, 5 disk reads, 10 files, 10 reads. This is read amplification. The price LSM trees pay for cheap writes. Without help, lookups would scale with the number of SSTables, which is unworkable. The next two ideas fix that. Every SS table on disk carries two small companions next to it, a Bloom filter and a sparse index. The Bloom filter is a compact bitmap that answers one question. Could this key possibly be in this file? It can lie in one direction only. It might say maybe when the key isn't actually there, but it never says no when the key is. So if the Bloom filter says no, we skip the file entirely. No disk read at all. The sparse index handles the maybe case. It's a small in-memory map that stores every 100th or every 1,000th key with its byte offset in the SS table. So we don't search the whole file. We binary search the sparse index, find the right neighborhood, and read exactly one disk block. Together, these turn a worst-case scan over many files into roughly one disk seek per relevant SS table. And Bloom filters mean most SS tables aren't relevant at all. That's how LSM reads stay fast despite all the layers. There's still a problem. SS tables keep accumulating. Every flush adds another file, and the disk fills with redundant data. The same key written again and again, plus tombstones for keys that were deleted. Compaction is the cleanup job. It runs in the background, picks several SS tables, and merges them into one new SS table. Because every SS table is already sorted by key, the merge is a streaming sorted merge. We walk all the input files in lockstep, take the smallest unseen key from any of them, and write it to the output. When the same key appears in multiple inputs, the newest version wins. Older versions are dropped on the floor. Tombstones are absorbed. If a delete marker meets the original key during compaction, both go away, the storage is finally reclaimed. When the merge finishes, the output SS table is published. The input SS tables are deleted. Disk usage goes down, file count goes down, and read amplification goes down with it. How you pick which SS tables to merge is a real engineering choice. Two strategies dominate. Size-tiered compaction groups SS tables of similar size. When you have, say, 4 small files, merge them into one medium file. 4 medium files merge into one large file, and so on. Cassandra uses this by default. It's cheap on writes, each key is rewritten only a handful of times, but a single point lookup might still consult several overlapping files. High space and read amplification. Leveled compaction is the other school. SS tables are organized into numbered levels. Within a level, files have non-overlapping key ranges, so a key lives in at most one file per level. Each level is roughly 10 times bigger than the one above. RocksDB and LevelDB use this. Reads are tight, at most one file per level, but every key gets rewritten many times as it migrates downward, so write amplification is high. That's the trade. There's no free lunch. You get to pick which kind of amplification hurts least for your workload. Here's a strange consequence of immutability. You can't delete a key in place. The SS table that holds it is frozen on disk. We promised never to modify it. So in an LSM tree, a delete is just another write. We append a tombstone, a small marker that says, this key is dead. The tombstone goes through the normal hot path. MemTable Write-Ahead Log eventually flush to its own SS table. Reads honor it. When a lookup walks the SS table's newest to oldest and meets a tombstone, it stops and returns not found, even if older SS tables still hold a real value for that key. So a deleted key takes more disk space than it had before, until compaction runs. When compaction finally merges the tombstone with the older live value, both rows are dropped and the space is reclaimed. This is why heavy delete workloads can balloon LSM storage temporarily. The deletes don't free space. Compactions do. Pull it all together, and you have a clean pattern. Write to the MemTable in RAM. Append to the write-ahead log on disk. When the MemTable is full, flush it as an immutable sorted string table. Reads merge across MemTable and SS tables, newest first, helped by Bloom filters and sparse indexes. Compaction runs in the background, rolling smaller files into bigger ones, dropping overwrites, and reclaiming tombstones. That pattern powers a lot of the storage you've used. RocksDB, Cassandra, LevelDB, HBase, ScyllaDB, and the storage engines underneath plenty of newer time series and event databases. LSM trees are the right pick when writes outnumber reads, when ingestion is bursty, when you're storing time series, logs, or any kind of append-heavy workload. The trade is honest. Writes are cheap, sequential, predictable. Reads pay a little extra to merge across levels. Compaction does the housekeeping, and the disk arm finally gets to rest. Buffer, flush, merge, repeat. That's how LSM trees actually work.